Welcome to another lesson of Math 1314 College Algebra. In this lesson, we will be discussing section 5.5, Zeros of Polynomials. In this section, we will evaluate a polynomial using the remainder theorem. We will use the factor theorem to solve a polynomial equation. We will use the rational zero theorem to find rational zeros, and we will find the zeros of polynomial functions. Let's jump right in and get started. We need to start first with a theorem, and that's the remainder theorem. The remainder theorem says that if a polynomial f of x is divided by x minus k, then the remainder of that division is the value f of k. Okay? So if we're given a polynomial function f, how do we evaluate the function at x equals k using the remainder theorem? So, given a polynomial f, evaluate f of x at x equals k using the remainder theorem. Well, the first step that we do is we use synthetic division to divide the polynomial by x minus k. Then, whatever our remainder is the value f of k. Let's jump in and try an example. In this example, we want to use the remainder theorem to evaluate f of x equal to 2x to the fifth minus 3x to the fourth minus 9x cubed plus 8x squared plus 2 at x equals negative 3. So what we need to do is we need to use synthetic division to divide the polynomial by x plus 3. So we end up with the minus 3 in the division. So we'll first create the columns that we need. Remember, even though we don't have a coefficient in front of x, we still need that column there. So we'll use 2, negative 3, negative 9, 8, 0, and 2. And in our division, we'll use the number negative 3, which is where we're trying to evaluate. We'll bring down our 2. And we have 2, so negative 3 times 2 gives us a negative 3. Oops. Not negative 3, negative 6. We add those together, we get negative 9. Negative 3 times negative 9 is a positive 27. Negative 9 plus 27 is 18. 18 times negative 3 is negative 54. 8 plus 50, negative 54 is negative 46. Times negative 3 is 138. And 138 times a negative 3 gives us negative 414. Rewrite that. We add those together, and our remainder in this case will end up being negative 412. Okay, remember we dropped down a degree, so this is x to the fourth, x to the third, x squared, x, our constant, and then finally our remainder. So r is equal to negative 412, and f of negative 3 is equal to negative 412. Let's try another example. We'll use the remainder theorem to evaluate f of x equals x cubed minus 21x squared plus 147x minus 343 at x equals 7. So we'll do our columns. We'll have our x squared, or our x cubed, our x squared, our x, and our constant. And we want to evaluate at 7, 1, negative 21, 147, and negative 343. Okay, we bring down our 1. We get 1 times 7, which is 7. Negative 21 plus 7 is negative 14. Negative 14 times 7 is negative 98. 147 plus a negative 98 is 49. 7 times 49 is 343. And negative 343 plus 343 is 0. So since our remainder is 0, f of 7 is 0, and we know that this is an x-intercept, so 7, 0 is an x-intercept. We have a 0 at x equals 7, and we know that x minus 7 is a factor of our original function. So x-intercepts, zeros, and factors of our functions, that really means the same thing. Zeros, x-intercepts, solutions, roots, those words are all talking about the same thing. Okay? So let's now move on, and we'll talk about finding zeros of a polynomial. We now need to discuss the factor theorem so we can go about solving a polynomial equation once we are given a factor. So the factor theorem says that k is a zero of f of x if and only if x minus k is a factor of f of x. So really what this means is exactly what we've been working on, is that if we're given something that we want to test for being a zero using synthetic division, if we know that k is a zero, then we also know that x minus k is a factor, and vice versa. So if we're given a factor and a third degree polynomial, how can we use the factor theorem to factor that polynomial? Well, the first thing we do, write that out, given a factor and a third degree polynomial, we want to use the factor theorem to factor the polynomial. So the first thing we do, as in the previous example, we need to use synthetic division to divide the polynomial by x minus k. And confirm that our remainder is 0. Then what we'll do is write that polynomial as the product of our newfound factor x minus k and the quotient that we found in the synthetic division. So write the polynomial as the product of x minus k and the quotient. Then, once we have a quadratic, we want to factor that quadratic if possible. And then finally, write the polynomial as the product of its factors. Okay, let's try an example. In this example, we want to use the factor theorem to find the zeros of f of x equals x cubed plus 4x squared minus 4x minus 16, given that x minus 2 is a factor of the polynomial. So the first thing we want to do is to do synthetic division to divide the polynomial by x minus 2. Okay, so the first thing we do is we create our columns, our x cubed, x squared, x, and constant. We can write in our coefficients, which are 1, 4, -4, and -16. And then we're going to divide by 2. Have that there. Bring down our 1. And we get 1 times 2, which is 2. 4 plus 2 is 6. 6 times 2 is 12. -4 plus 12 is a positive 8. And 8 times 2 is 16, which means our remainder is 0. Okay, so our next step is to write the polynomial as a product of x minus 2 and the whatever the quotient was. So f of x is equal to x minus 2 times, again, we step down 1 power from our highest power, which will be 2, and we use that coefficient here for that term, so we get 1x squared, or just x squared, plus 6x plus 8. Okay, now we want to factor x squared plus 6x plus 8. How do we do that? Well, let's look at the factors of 8. Because our leading coefficient is 1, we only have to look at that. So our factors of 8 are 1 and 8, 2 and 4. And our sums there are 9 and 6. So the pair we want is the 2 plus 4. So f of x is equal to x minus 2 times x plus 2, x plus 4. Okay, so that means that our zeros happen when we plug in, or when we set each of these factors equal to 0. So x minus 2 equals 0, or x plus 2 equals 0, or x plus 4 equals 0. So that means that x could be equal to 2, or x could be equal to negative 2, or x could be equal to negative 4. So those are our three zeros. Again, we started with a third degree polynomial, so we expect to get 3 zeros out of this function. Okay, so we knew that at the very beginning that x minus 2 was a factor, and we found out that our factors for the entire function are x minus 2, x plus 2, and x plus 4, and that our zeros were x equals 2, x equals negative 2, and x equals negative 4. Let's try another example. In this example, we want to use the factor theorem to find the zeros of f of x equal to 2x cubed minus 9x squared plus 13x minus 6, given that x minus 1 is a factor of the polynomial. Again, we want to use synthetic division, so we create our columns, x cubed, x squared, x, and our constant. Our coefficients are 2, negative 9, 13, and negative 6. And the thing we're dividing by, in this case, will be 1. We'll bring down our 2. We can get started with the synthetic division. 2 times 1 is 2. Negative 9 plus 2 is negative 7. Negative 7 times 1 is negative 7. 13 plus a negative 7 is 6. And then 6 times 1 is a positive 6. Negative 6 plus 6 gives us a remainder of 0. So that tells us for sure that x minus 1 is a factor and that x equal 1 is a 0. So we want to find the rest of the factors. So we need to write f as x minus 1, the factor we just divided out, times our quotient, which is 2x squared minus 7x plus 6. And now we want to try and factor that quadratic on the right, the second factor there. And we can do that using the AC method. And so we look at a times c, which is 2 times 6, or 12. So factors of 12. And it gives us a negative value, so both factors have to be negative. So negative 1 and negative 12, negative 2 and negative 6, negative 3 and negative 4. Those are our factors. The sums, negative 1 and negative 12 are negative 13, negative 2 and negative 6 is negative 8, and negative 3 and negative 4 gives us a negative 7. So the factors that we want are the negative 3 and the negative 4. So we can break that up using the factoring by grouping. So f of x is equal to x minus 1 times 2x squared minus 4x minus 3x plus 6. Do another rewrite there. We can factor out a 2x and get x minus 2. And we can factor out a negative 3 and get x minus 2. So our final step is to write it as x minus 1. We have a common factor of x minus 2. We're left with 2x minus 3. So what we know is that one of those factors has to be 0 for us to get a 0 out of it. So x minus 1 equals 0, or x minus 2 equals 0, or 2x minus 3 equals 0. So this one gives us that x equals 1, or x equals 2. In this case, I will do the steps. I'll add 3 to both sides to get 2x is equal to 3. Divide both sides by 2. So x must be 3 over 2. Okay? So that tells us that our zeros are x equals 1, x equals 2, and x equals 3/2. Rewrite that. Okay. Now we'll move on and discuss using the rational zero theorem to find rational zeros. Now we need to talk about the rational zero theorem. The rational zero theorem states that if a polynomial f of x has integer coefficients, then every rational zero has the form P over Q, where P is a factor of the leading coefficient. Sorry, P is a factor of the constant term. And Q is a factor of the leading coefficient. Let's try that again. Okay, now that we have the rational zero theorem, let's try an example. Okay, in this example, we want to list all the possible zeros of f of x equals 2x cubed plus x squared minus 4x plus 1. So the first thing that we want to do is we want to determine all of the factors of our constant term, which is 1, and all the factors of our leading coefficient, which is 2. Okay, so our possible factors of P, which are, P is our constant term, P equal to 1, are 1 and negative 1. Okay, and then our factors of, let's go underneath here, our factors of Q, which is our leading coefficient, equals 2. So our factors there are 2 and negative 2. Okay, so any combination of these factors gives us our possible rational zeros. So potential zeros are 1/2, negative 1/2, and let's see, I think that's all. We get plus or minus 1/2. Okay, so those are our two potential rational zeros, and that's all that we get. So what we do is we list the factors of P and the factors of Q, and we see what our possibilities are. Let's try one more example. In this case, we want to list all possible zeros of f of x equal to x to the fourth minus 3x cubed plus 4x plus 4. Okay, so we look for factors of P. P is our constant term. So our potential factors there are factors of 4. So factors would be 1, 2, and 4. Q, well, what is Q? Well, Q is just 1. So those are the factors that we get. So our possibilities are plus or minus 1. So we start there at 1. Plus or minus 2, which would be 2 over 1. And plus or minus 4, which would just be this one. Okay, so potential are potential zeros plus or minus 1, plus or minus 2, and plus or minus 4. Now, the next thing we will want to do is determine which possible zeros are actual zeros by evaluating each case. And the way we would do that is with synthetic division. So our next step is to perform some synthetic divisions and actually find zeros. In this example, we want to use the rational zero theorem to find the rational zeros of f of x equals x cubed minus 5x squared plus 2x plus 1. So what is our p? Well, our p is our constant term, and our q is the coefficient on our leading term. So factors of p over factors of q, we get, well, the coefficient of the constant is 1, so we get 1 over, again, or 1, so our possibilities are plus or minus 1. So let's do some synthetic division, create our columns, and our coefficients are 1, -5, 2, and 1. We'll start out trying to see if 1 is a 0, so we bring that down. So 1 times 1 is 1, -5 plus 1 is -4, 1 times -4 is -4, 2 plus a -4 is -2, -2 times 1 is -2, and 1 plus a -2 is -1. So x equals 1 is not a 0. Okay, let's try another. Same thing, x cubed, x squared, x, and the constant. 1, -5, 2, and 1. And this time, our other factor is -1. Bring down our 1. And 1 times -1 is -1. Gives us -6, +6, 8, and then -8. So 1 plus -8 is -7. So x equals -1 is not a 0 either. So what does this tell us? Well, it tells us that in both cases, we have no rational zeros for this third degree polynomial. That means that all of our zeros are not rational. Let's try another example. Okay, a lot of times what we'll be given, instead of having a function, is we'll be given just an equation that's set equal to 0. So we can, since this is set equal to 0, we solve it in the same way, and we're looking for the zeros of this polynomial equation. Okay, so the first thing that we can do is try and figure out at least one of the zeros. Now, there are a number of ways you can do this. One of the easiest ways is to plug it into a graphing calculator and look at the table. And you want to look for a y value that's equal to 0, and then you use that x as the 0. So something else we want to look at with respect to this equation is our leading term. which is x cubed. Our degree of that is 3. Our leading coefficient is 1, which is positive. And we have an odd degree. So we know our end behavior is down to the left and up to the right. So our first zero, if you look in your calculator, you could probably find one at x equals -3. Now again, this has degree 3, so we should actually expect to see 3 zeros. Okay, so the first thing we want to do is to divide out that -3 using synthetic division. So we'll write our columns, x cubed, x squared, x, and then our constant. Our coefficients are 1, -3, -10, and 24. And we're dividing out that -3. Bring down our 1. So we have 1. 1 times -3 is -3. -3 plus -3 is -6. -3 times -6 is -18. -10 plus a -18 is -28. Actually, check that. It should not be -28 because when we multiply -3 times -6, we actually get a positive 18, not a negative. So a -10 plus 18 gives us 8. 8 times -3 is -24. 24 plus a -24 is 0, which is exactly what we would expect. We need our remainder to be 0. Okay, so we found that. So what we're left with is a 1x squared minus 6x plus 8 equal to 0. Well, now that we've found 1, 0, can we factor out the others just using the AC method? Well, we're looking for the factors of 8. And we have a negative on our middle term. So we need both factors to be negative. So -1 and -8. -2 and -4. And then our sums are -9 and -6. So we want the last pair. And what we get is x minus 2, x minus 4 equal to 0. So that gives us our zeros, which are 2 and 4. So if we were to write this all out in fully factored form, it would be x plus 3, x minus 2, x minus 4 equal to 0. Okay, so we found our zeros just based on that. And that's sort of how you do it. Again, we use the calculator to find this first 0, but we could have just started with the rational zero theorem and used P and Q to figure out what all of our possibilities were, and then work through those systematically to find which ones are zeros and which ones are not, using synthetic division. Okay, so there's that one. Let's try another example. Okay, in this example, we want to find the zeros of f of x equal to 2x cubed minus 7x squared plus 4x plus 4. And I think we should do this one systematically and find the zeros using the rational remainder theorem, the rational zero theorem. Okay, so we need to look at our P and Q, and P is the coefficient on the constant term, and Q is the coefficient on the lead term. So we want to look at the factors of P over the factors of Q and those are, so for 4 we have 1, 2, and 4. And Q is 2, so it's just 1 and 2. So possible zeros are 1 over 1, or just 1, so plus or minus 1, 2 over 1, so plus or minus 2, 4 over 1, plus or minus 4, and then we switch our denominator now to be this 2, so we have plus or minus 1/2, plus or minus 2/2, which is just 1, which we already had, and plus or minus 4 over 2, which is 2. So that's our last one. So we have 2, 4, 6, 8 possibilities for zeros. Now our leading term is 2x cubed. Our degree is 3, which is odd. Our leading coefficient is 2, which is positive. So what we know about our end behavior is that on the left we go down and on the right we go up. Okay, so let's try and see if we can find the zeros. Let's build our synthetic division. We have x cubed, x squared, x, and constant. Our coefficients are 2, -7, 4, and 4. And then we're dividing out, and let's just go ahead and start with the smallest, which would be a -1/2. -1/2 is our smallest value. And then we'll drop down with our 2 and get it going. So -1/2 times 2 is -1. -7 plus a -1 is -8. -1/2 times -8 is a +4. 4 plus 4 is +8. -1/2 times 8 is -4. And 4 plus a -4 gives us 0. So x equals, let's go ahead and write out a place for our zeros. X equals -1/2 is a 0. Now again, we should expect to see 3 total since we have a third degree polynomial. Okay, now we have 2x squared minus 8x plus 8 as our remaining quotient. Can we factor that? Well, let's try it. Let's try the AC method. AC is equal to 2 times 8, which is 16. And so we need factors of 16 that give us a -8, so we need both factors to be negative. So -1 and -16, -2 and -8, -4 and -4. Our sums would be -17, -10, and -8. So we can choose this last pair, and we get 2x squared minus 4x minus 4x plus 8. In the first grouping, we can factor out a 2x and get x minus 2. In the second grouping, we can factor out a -4 and get x minus 2. And so we're left with 2x minus 4 times x minus 2. So our other zeros would happen when 2x minus 4 is equal to 0, or when x minus 2 is equal to 0. We can add 4 to both sides, to get 2x equals 4. Divide both sides by 2, so x equals 2, or add 2 to both sides here, x equals 2. So we got x equals 2 in both cases. What does this actually mean? Well, what this means is that we have two zeros, x equals 2 and x equals 2, where we have a multiplicity of 2 in with that solution. So this is multiplicity 2. So there's a bounce, as we've seen before, and that happens at the point 2, 0. Now, the other 0, x equals negative 1/2, has multiplicity 1, and so it passes through. Now, it could have been the case that we didn't pick a 0 the first time that we chose one of these possible values. But if we had, we would have just repeated the synthetic division multiple times until we found one, and then we try and factor. Now, if we had started with 2, we might have ended up getting that 0 and then missing zeros a lot of the other time, especially if we made a mistake in the factoring or something. So that is finding the zeros using synthetic division. Let's try one more example after this. I do want to make one more note, and that is that a lot of times you can look at a graph and find one of the zeros or find close to where it's at. You could use your graphing calculator or a graphing utility like Desmos. You could either do that visually to find where there was a multiplicity 2, where there was a bounce or something like that, or if you were to find multiple zeros using the graph, you could also use the table like I mentioned to find at least your first point or your first 0. So that's a good pathway for when you're given a problem on a test, that you can just go and look at the table in the graphing calculator to find a 0, at least one 0 if it exists. In this example, we want to find all the complex zeros of f of x equal to 3x cubed minus 4x squared plus 11x plus 10. Okay, so we can plug this into our graphing calculator and look at the table to see if we can find a 0, or we could take a look at the graph and see if that helps. But after looking at the table, I'm not finding just an easy rational solution that's a whole number. So I think we should probably use the P and Q of the rational zero theorem. Here's our P and here's our Q. So factors of P over factors of Q. So that gives us, what are our factors of 10? Well, we have 1, 2, 5, and 10. And then our denominators, factors of Q, which would be factors of 3, which are 1 and 3. So our potential zeros are 1 over 1, which is 1, so plus or minus 1. 2 over 1, which is plus or minus 2. 5 over 1, which is plus or minus 5. 10 over 1, which is plus or minus 10. And then we change our denominator, and we get plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 5 over 3, and plus or minus 10 over 3. So where do we want to start? Well, I think in this case I would want to try a whole number, just because I think the synthetic division would be easier. So let's try that. We'll just start with a positive 1. And so we'll write out our x cubed column, our x squared column, our x column, and our constant column. And then our coefficients are 3, -4, +11, and 10. And we're dividing out 1. Bring down our 3. So 3 times 1 is 3. -4 plus 3 is -1. 1 times -1 is -1. 11 minus 1 is, or 11 plus a -1 is 10. And 10 times 1 is 10. So we get 20. So our remainder is 20. So f of 1 would give us 20. So that is not a 0. So I'll just take and mark out that +1. What about -1? All right, same setup. So I'll just copy all of this. And so now we have a -1. Bring down our 3. We'll do another synthetic division. -1 times 3 is -3. -4 plus -3 is -7. -1 times -7 is +7. 11 plus 7 is 18. -1 times 18 is -18. And 10 plus a -18 gives us a -8, which is not 0. Okay, so we can cancel out the -1 also. So we can go through all of these and see if they all work. But to make our time a little easier, I've gone through and looked at all of our possibilities from -10 to 10, and none of the whole numbers work. So we won't do all of those synthetic divisions just to find that. Let's try one of our fractions. So same story, except this time we're not going to use 1. Let's try and use how about -1/3? So we can bring down our 3. -1/3 times 3 gives us -1. -4 plus -1 is -5. -1/3 times -5 gives us -5/3. -5/3 plus 11 gives us 28/3. 28/3 times -1/3 gives us -28/9. Okay, and then we add that to 10, and we get 62/9, which is definitely not 0. Okay, so that one didn't work. Let's try one more. And instead of -1/3, let's try -2/3. So we'll bring down our 3 again. So 3 times -2/3 gives us -2. -2/3 times -2 gives us 4/3. 4/3 plus 11 gives us, I'm sorry, I didn't add those yet on this one. Goodness. -4 plus a -2 is -6. Then -6 times negative 2/3, which gives us 4. 4 plus 11 is 15. 15 times negative 2/3 gives us a negative 10. 10 plus a negative 10 gives us 0. So you've got to be very careful with your arithmetic when you're doing synthetic division. But we found a remainder of 0. So that means x equals negative 2/3 is a 0 of this function. Okay, so we factored it out, and so what we're left with is 3x squared minus 6x plus 15 and we want to find the zeros of that part, so set it equal to 0. Now we can factor out a 3, and we're left with x squared minus 2x plus 5 equals 0, or just x squared minus 2x plus 5 equals 0. And if we try to factor this, what are the factors of 5 that when we add we get negative 2? Well, the factors of 5 are 1 and 5, and they'd have to both be negative, which won't give us negative 2. So it looks like we're going to have to break out the old quadratic formula for us to be able to solve this. So our a, b, and c, our a is 1, our b is negative 2, and our c is 5. Remember, those are the coefficients of our quadratic and standard form. So x is equal to negative b, which is negative of negative 2, plus or minus the square root of b squared, so negative 2 squared, minus 4 times a, which is 1, times c, which is 5. Let's move that over just a bit. We'll rewrite that 5 so we're clear on what it is. All over 2 times a, which is just 2. So that's equal to 2 plus or minus the square root of negative 2 squared, which is 4, minus 4 times 1 times 5, which is minus 20, over 2. Okay, simplifying further, 2 plus or minus 4 minus 20 is negative 16, so the square root of negative 16 over 2, which is 2 plus or minus 4i over 2, because the square root of 16 is 4 and the square root of negative 1 is I. So we have 2 plus or minus 4i over 2, or 1 plus or minus 2i. So our other zeros in this case are actually imaginary. So our graph would only cross through the x-axis one time, and that would be at x equals negative 2/3. And our other zeros are 1 plus 2i and 1 minus 2i. Our zeros are x equals negative 2/3, x equals 1 plus 2i, and x equals 1 minus 2i. Now, something else to note is that this is our only x-intercept. Again, it will only cross once. Now, we could plug into our original equation, which was this guy, and we can find our y-intercept if we were trying to graph it. So we have, switch colors here, y equals 3 times 0 cubed minus 4 times 0 squared plus 11 times 0 plus 10. Well, the 3 0 cubed goes away, the negative 4 0 squared goes away, the 11 times 0 goes away, and we're left with just the plus 10. So finally, our y-intercept is the point 0, 10. Okay, so now we have the direction of the end behavior. We know all of our zeros, even though 2 are imaginary. We know that we have multiplicity 1, so this 0 just passes straight through the x-axis, and we have the y-intercept. So let's take one more step and go look at this graph in Desmos and see what it looks like. So here we are in Desmos, and as you can see, this graph looks like it's just pretty close to, it's a curve, but there's not a whole lot of curve to it. It seems pretty basic. We can see that we're crossing the x-axis. That looks like negative 2/3, right where it should be. It's the only place it does cross, and then it crosses the y-axis up at 0, 10, so we got that correct. And then I'll zoom out quite a bit, and you can see there is a little bit of curvature. Curves up to 0, goes through, and then goes up to infinity. Okay, so that's generally what our graph looks like. So in this lesson, we've discussed the zeros of polynomial functions, how to use synthetic division to find those, the rational zero theorem, the factor theorem, and the remainder theorem. And that concludes section 5.5. Thanks for watching. Good luck on your homework, and I'll see you in the next one.